Hello everyone. I hope I am audible and my screen is visible. So let's start the session. So welcome to the live session for the course Introduction to Semiconductor Devices. I am Ananya. I am the TA for this session. I am a PhD student in the Department of Electrical Engineering, IIT Kanpur. If you don't know me, I hope you know me by now. I have conducted 11 live session earlier for this course, and we will have one more live session for week 12 that will be on next Tuesday. So this is an extra session actually. So I have few questions. I tried to take few like one or two questions from each week. Obviously it is a 1 hour session, so I will not be able to do a lot of problems, but I have tried to compile a few questions that covers topics from most of the weeks. Okay, so let's start. There might be some background noises today. I'm so sorry for that. I don't know, there is some problem with my settings. I cannot use a earphone. I don't hear anything if I use a earphone. Okay. Let me write down the first question. So this question is from initial week. We have studied about quantum mechanics in this course, little bit of quantum mechanics, and from that we learned how we get the band diagram or band gap of semiconductors. Okay, so this question is on Schrodinger's equation. Okay. Consider an electron confined in an infinite square well. Okay. Square well of width 1 nanometer. If an electron undergoes a transition from the first excited state from the first excited state, that is n equal to 2, so n is the quantum number, to the ground state and for ground state n is equal to 1. We know that n cannot be 0, right? We have solved Schrodinger's equation in infinite square well. When an electron undergoes this transition, it emits a photon. Okay, there is a change in energy between n equal to 2 state to n equal to 1 state. Okay, that energy is released in form of a photon. The question is, calculate the wavelength of the photon. Photon emitted during the transition. So we studied about Schrodinger equation. What is the Schrodinger equation? I will write it for one dimension. So what is Schrodinger equation? It contains the wave function of a particle, and normally we solve it for electrons and other quantum particles. So here we are discussing about wave function of an electron. Okay, and we solve the Schrodinger equation to get the solution, which is the wave function of an electron or any other quantum particles in a particular scenario. Okay. And that wave function actually contains information about the particles. For example, we can find out the energy, we can find out the momentum of the particle from the wave function. Okay. So the Schrodinger equation, in Schrodinger equation there is this wave function. If we are considering the wave function of one dimension, it can be in three dimension. Okay, I mean it is normally wave is in three dimension, but here we are considering a one dimensional scenario. Okay, infinite square well of width. So here we are considering the wave function in a one dimension, and I'm saying that it is a function of only x. It can be a function of xy or xyz, and then it also has a time dependent component. Wave changes with time. So we can write the Schrodinger equation by using both this space and time dependent component, but we normally take the time independent Schrodinger equation. Okay, so we will write the time independent Schrodinger equation, and that is minus h bar square by twice m d2 by dx2. I'm writing like not partial derivative. If it is a function of xyz, then I would have right partial derivative. Okay? D2 by dx2 plus v of x into psi of x is equal to e of psi x. Okay, this is time independent Schrodinger equation. What is h bar? This is the reduced Planck's constant. V is the potential, whatever the potential that electron is experiencing. In this case, infinite square well, so there is a potential well, that is the potential the electron is experiencing. It can be the potential of a crystal structure. We know that because of the atoms, the electrons will feel some potential. Okay, so we try to write it in a mathematical form to find the wave function of an electron inside of a crystal. Okay, based on that we get the band gap in a semiconductor, and how we find the band gap and how we get the band structure, that was discussed briefly in the initial 1 or 2 week for this course. Okay, so this is the potential Vx, whatever the electron is experiencing, and E is the energy of the electron. Now, what is the drill? We solve this. This is a second order differential equation. We solve this equation to find the wave function, and that wave function gives information about the electron. If it is a free particle, we know that if it is a free electron, then Vx is 0. The electron is not experiencing any force, any potential, so the equation will be minus h bar square by twice m d2 psi by dx2 equal to E of psi. Okay, this gives us, we can write it in this form, 1 by psi d2 psi by dx2 equal to minus 2m E by h bar square, and we write this term as minus k square. K square is the wave number, right? So the solution for this is an exponential function, e to the power ikx or it can be to the power minus ikx, or it can be combination of these two. That means either we can have a sinusoidal or cosine function. Okay, now for this case, what is the dispersion relation? What I mean by dispersion relation? It is the relation between E and K. So E and K relation is equal to h bar square k square by twice m. Okay. Now we know that for free electron the energy value can be anything, the K value can be anything. That means the energies are continuous. Now what happens in case of a potential well? Now instead of a free electron, if we have a electron in infinite potential well, so the well will look like this. Say this is my x direction. Potential in this region, in region 1 and 3, the potential is infinite, and the potential here is 0. Okay, and our electron is here. Okay, because it cannot move outside of this region because there is this infinite potential. Okay. So what is my wave equation in this scenario? So in case of infinite potential well, we know that our wave function, the solution of Schrödinger equation, the wave function, I am not going into the details of how we can solve it. We have done this in earlier weeks. So our wave equation is something like this: a sin kx plus b cos kx. Okay. Now we know that our electron cannot be present here in region 1 and region 3. So that means my wave has to go 0 at this x equal to 0 point and this say x equal to L point. Okay, length of the wave. So our wave function cannot directly go to 0. That means the wave in this side, in region 2 also, at this point it has to be 0, at this point it has to be 0, at x equal to 0 and x equal to L. So this we call it as a boundary condition, and based on that we solve, we use that condition that x at x equal to 0 and x equal to L, psi of x will be 0 and also derivative of psi of x is also 0. So based on that, what we get, our wave function we get as a sine n pi by L into x, and where n is 1, 2, 3, etc. Okay. So my k is n pi by L. Now our k is not continuous. It has discrete values where n equal to 1, 2, 3 and so on. When my n is k is quantized, we say that k cannot take continuous value. That means k is quantized. When k is quantized, we know that our energy values of the electrons are also quantized. So what is the energy levels? So En is h bar square kn square by twice m. It's similar to this, but in this case k is not continuous. Okay, so this is h bar square by twice m by n square pi square by L square. Right. So that means our electron cannot take any energy value. The energy values are quantized. Right. Now say this is my n equal to 1. You see the energy, if this is my energy scale, then this energy for n equal to 1 is non-zero. You can put n equal to 1, this will be a non-zero value. Then I will have some other n equal to 2, say this is the energy level, and for say n equal to 3, this is the energy level. The gap between these energy levels are not constant because it varies as n square. Okay, so if we have E1 for the first energy level, then the second energy level E2 will be n square into E1. Okay, so n square into E1, for E2 it will be 4E. Similarly for E3 it will be 3 square into E1, that means it is 9E1. So the gap, the difference between E1 and E2 and E2 and E3 is not same. So what is the difference between E2 and E1? This is 3E1, right? So here the question is that the photon will have same energy as the electron emits while it is traveling from n equal to 2 to n equal to 1. So that means the energy of the photon is E2 minus E1, right? An electron is moving from here to here, it will release energy in form of a photon. So the photon will have this much of energy. So let's calculate it. So what is E1? That will be h bar square pi square twice of m into L square. Okay. So H is Planck's constant 6.06 into 10 to the power minus 34. This is divided by 2 pi to calculate H bar, right, into 3.14 by 2. So Planck's constant is 1.055 into 10 to the power minus 34 into pi square 3.14 square divided by 2 into m is for electron 9.1 into 10 to the power minus 31 into L is given to us as 1 nanometer, right? This is given in the question as 1 nanometer. So into 10 to the power minus 9. Okay, this will be in joule because Planck's constant I am taking in, as in joule, so I have to divide it with Q1, 1.6 into 10 to the power minus 19 there is L square, so that is what I made mistake. Let me write it down, otherwise I am making mistake in calculation. And 0.055 into 10 to the power minus 34 into 3.14, and this is whole square divided by 2 in 0.1 into 10 to the power minus 31. If you are watching in YouTube, then please also calculate along with me. 18. So this will be, and then this will be in joule, okay, and in electron volt, E1 in electron volt will be E1, we multiply with 1.6 into 10 to the power minus 19. So this will be 0.3768 eV. So what will be the wavelength of photon? This will be, we know this relation lambda is equal to 1.24 by delta E, which is in our case 1.24 into 3 into E1, right? This much of energy is being emitted when an electron is moving from n equal to 2 to n equal to 1. So this value will be, here we will get lambda in micrometer if we use this expression, okay? So this will be around 1.1 micrometer. Okay, this is the value. So let's take the next question. Question is, calculate the de Broglie's wavelength of a particle. Consider an electron traveling at the velocity of 10 to the power 7 centimeter per second. So this is equal to 10 to the power 5 meter per second. Okay. So let's solve it. We know what is de Broglie's hypothesis. It says that every particle has a wave nature, so dual nature of matter, right? So a particle also have a wave nature and wavelength associated with it, and that wavelength is lambda is equal to h by p, where h is the Planck's constant and p is the momentum, which is m into v, right, velocity. So what this value will be? Planck's constant 6.626 into 10 to the power minus 34. This is in joule second, and then m is 9.1 into 10 to the power minus 31, and velocity is 10 to the power 5. I am keeping everything is in standard unit. Okay, so this unit is kg meter square per second to the power minus 1. We know that this is joule second, so joule is kg meter square second per minus 2. This is the unit, and this is kg, and this is meter per second. Okay, so my unit comes as meter, which is the correct unit for wavelength. Okay, I just always do a dimensional check. So this value will be 6.626 into this is 7.28 into 10 to the power minus 9 meter. So lambda is equal to 7.28 nanometer. Now electrons, you can see that electrons are very small particles. So with respect to the size of the electron, this lambda is it's comparable, right? So that is why the wave nature of particle, especially for quantum particles which are very small, those are important. It's like every particle has this wave nature. Okay, you can calculate this lambda for suppose a car, or for like some some object from macroscopic world. So you can take calculate it for a car, say mass, you can say maybe, I don't know what is the weight of a car, 1000 kgs, you can google it. And then velocity maybe like say 60 km per hour, and then you can find lambda. That lambda will be very small, negligible compared to the size of the car. Okay, that is why this wave nature, this dual nature, these are not important for macroscopic world, but these are very important when we talk about quantum particles, for very, very small particles. Okay. Next, this is a question from GATE 2021. I think this is not from EC, this is from physics. So the question is, the donor concentration in a sample of N-type silicon is increased by a factor of 100. Okay, donor concentration is increased. Is donor concentration, what is the notation we use? ND, right? Assuming that the sample is non-degenerate. So remember what is non-degenerate semiconductors. In these semiconductors, the doping concentration is not that high, was not discussed in detail, but all the equations that with it derive, these are valid for for most of the equation that we derived in the semiconductor, like initial part of the course. Those are valid for non-degenerate semiconductors, not valid for degenerate semiconductors. Okay, for example, mass action law, where we consider that n into p equal to ni square, that is also valid. This is for non-degenerate semiconductors. Okay, the doping concentration is actually lower, and yeah, doping concentration is not comparable to the density of state, roughly. So we are considering that it is a non-degenerate semiconductor. That means all the equations that we have discussed, those are valid, and the donor concentration is increased by a factor of 100. What is the shift in Fermi level? To write it in milli electron volt at 300 Kelvin. Okay, and given that kT at is equal to 25 milli electron volt at 300 Kelvin. So we know that this is the band diagram of a semiconductor. This is EC, EV, edge of the conduction band, edge of the valence band. If it is an intrinsic semiconductor, then the Fermi level lies in the middle, approximately in the middle. There is a slight difference. What is the difference that we have discussed earlier? But most of the cases we consider it in the middle, and which is true, like mostly. I mean, it does not has a lot of difference. Okay, and this is the intrinsic Fermi level if the semiconductor is intrinsic. If there is n-type doping, there are donors, then the concentration of electron is higher, so the Fermi level moves close towards the EC. Okay, so say this is EF. Now how close the Fermi level will move towards EC, that depends upon the doping concentration. Okay. What Fermi level indicates, this is like a water level, that till this much electrons are filled. Okay, so not exactly, I mean, we know that there are no electrons in the band gap, but this indicates that how many number of electrons are present, or what is like the average energy of electrons. Okay, so if it is an n-type semiconductor, then the number of electrons is more, so the Fermi level is high. If we add more and more number of donors, then the Fermi level will move closer to EC. Okay, so the question is, we have to find what is the shift in the Fermi level if we increase the doping concentration by 2 order. 100 is like increase the doping concentration by 2 order, 10 to the power 2, right? Okay. So we know this equation. This is true for non-degenerate semiconductors. EF minus EI difference between the Fermi level and the intrinsic Fermi level, we know this equation kT ln of nd by ni. Okay, I think by now you remember this equations. Okay, and say this is for the first semiconductor, and when we increase the doping, then EF2 minus EI become kT ln of 100 of nd by ni. Okay, this was good physics 2021. So EF2 minus EFI is one is kT ln of 100. So what will be this value? So this is 25 millielectron volt into ln of 100 is 4.6 millielectron volt. So 115.13 millielectron. Now there is this one question. This is a bit confusing when I tried for the first time also, so that is why I am taking this. So the question is, for every 10-degree increase in temperature, the reverse saturation current of PN junction will increase by, there are few options. So the solution is, if we simply use the equation, then there will be an error. So what is reverse saturation current in PN junction? The expression is QDN by Ni square by Ln into Na, right? And plus QdP into Ni square by Lp into Nd. So basically this is N in P side and this is P in N side. Right? So this reverse saturation current depends on this temperature as well as the band gap, because it depends on Ni. But what happens when there is a change in temperature? Okay, so we know there is this Ni square is N into P if we use mass action law. So that is Nc Nv exponential by C by Kt, right? Yeah, it's like that. So we cannot directly use this here, because this is not for like PN junction. What happens in PN junction in we have this depletion layers, and what happens when there is an increase in temperature, there will be more number of generation of electron and hole pair, and that is the main mechanism how the reverse saturation current is increasing. Okay, so the electron and hole pairs and the number of electron and hole pairs are increasing, and that is how the Ni, basically the current is increasing because Ni is increasing. So what happens as temperature increases? EHP generation happens. In depletion region. And because number of carriers are increasing, so that's how Ni is increasing, and in that way this gives us Iz actually not Iz, so the reverse saturation current actually directly proportional to Ni. Okay, because as the number of carriers are increasing, current is increasing. Okay, so now we will see, this is the same question, right? In the Ni term, we have this NC/Nv exponential minus Eg by kT. So this is for Ni square. So Ni is proportional to, so NC/Nv, if you remember, there is this t to the power 3 by 2 term. Okay, please go to the lecture notes from earlier sessions. So this is 2 into Mn star into kT, that is this term. Okay, so it has temperature to the power 3 by 2 dependency. Yeah, there will be, so Ni is proportional to t to the power 3 by 2. Okay, there are just two terms, Nc and Nv, but this is square. So overall we will get this. And also from this we can write our initial temperature, say it increased to 310 degrees Celsius, 10 Kelvin, initially it was 300. So there is a factor increase of around 1.05. Okay, now we have this exponential term also. So say we have initially so I'm trying to find the factor by which it increases. Eg by 2k, because this is square, so there will be 1 by 2 term. This will be because it is exponential, so when I do the the division, Ni at 310 Kelvin by Ni at 300 Kelvin, so this will be minus, so this will be 1 by 310 minus 1 by 300. Right? Okay, so roughly let's calculate. So this is 2 into 6, 6, 1, 6, 6. So this is the K constant, I mean Boltzmann constant in electron volt per Kelvin. Okay, and this is this is minus 1.07 into 10 to the power minus 4. So this is roughly into 1.12 divided by 0.69. So exponential of this will be exponential of 0.69. So this is approximately 2. So the current because this exponential term will actually dominate, so this is 1.05 and this is 2, so ultimately the exponential term will dominate, so Ni increases by 2 times. Okay, that will also give us current increases by also 2 times. This is because our NP naught and these are increasing due to electron and hole pair, and how the based on electron and hole pair it increases it by 2 times. Okay, please go through it once again if there is confusion and doubt. Think it through it once again. I think it will be clear then. Okay. Calculate this one. This is asked. This is a question in GATE 2022. So the question is, the ideal long channel NMOS and PMOS threshold voltages are 1 volt and minus 1 volt respectively. The MOSFET substrates are connected to their respective sources. That means there is no body bias voltage. Okay. have to calculate V1. The circuit is given like this. This is for NMOS. This is 5 volt connected to gate. This is V1. We know that this is the drain terminal and this is the source terminal. Drain is connected to the higher voltage for NMOS, and there is a capacitor connected to this, which is 1 microfarad, and initially the capacitor is discharged. Okay, there is no charge across this in this capacitor. Okay, so this is my source terminal, and I have this PMOS. Gate is minus 5 volt. This is 5 volt. In the question it is not indicated as source, but we know that this is the source because this is PMOS, and this is the voltage here. Again it is connected to this capacitor, which is 1 microfarad. So this is NMOS, this is PMOS. So we have to calculate V1. Now for NMOS, initially this is discharged, that means this source is connected to this point, so this is 0 volt, right? So VGS, we have to see whether this is turned on or not. So VGS is greater than or equal to VTH or not. So VGS is 5 minus 0, that means 5 volt, and it is greater than 1 volt, right? What is the threshold voltage for this? So this transistor is on. When the transistor become on, so that means there is a flow of current from drain to source. So this capacitor will get charged. Okay, so current is flowing, the capacitor is getting charged, so it will get start and the voltage will increase. Let's say the voltage is increasing from 0 volt. Now say the voltage is 3 volt. So if this is 3 volt, the source terminal is 3 volt, then what is VGS? 5 minus 2, 5 minus 3, that is 2 volt. So it is, this condition is still satisfied. But what happens if V1 or the source voltage or the capacitor is charged till 4 volt? So when it is 4 volt, then this VGS 5 minus 4, that will be 1 volt, right? Which is equal to the threshold voltage. Now this transistor will be still on in this case, but the voltage cannot increase beyond 4 volt. V1 is equal to 4 volt. It will start with 0 volt because initially the capacitor is charged. It will charge, the voltage will increase. As soon as the voltage becomes 4 volt, it cannot charge more than that. It cannot charge, even though we are applying a 5 volt here, it cannot charge till 5 volt, because if it becomes 5 volts, let's say if it becomes 5 volt, then this condition will not satisfy. So our MOSFET will turn off and the capacitor will start to discharge. Okay? So the maximum voltage of V1 is equal to 5 volt because the threshold voltage is 1. Okay. So in case of NMOS, if we are using it, so if you must have studied about pass transistor, this concepts. Okay. When we use it NMOS as a pass transistor, the source terminal, whatever load you connected to the source terminal, the maximum voltage you can get is whatever our VDD applied minus, or VDS, whatever the VDS is applied, minus the threshold voltage. This is the maximum voltage we can get. Okay, because beyond this point our NMOS will turn off. Now that is why NMOS are not a very good pull-up transistor. What pull-up transistor means? Pull-up transistor tries to connect the source terminal or the load terminal to the highest voltage. It is pulling up to 5 volt. But NMOS cannot be a good pull up transistor. It can pull up till VDS minus VTH value. That is why, if you remember, in case of CMOS circuit, we make these two blocks. Okay, here this will be connected to VDD and this will be connected to the ground. This part which is pulling up our load will be connected here. Say if I'm connecting a resistor as a load, then the pull up part of the circuit is made using NMOS, and pull down part of the transistor is made using so this is made using PMOS. Sorry, this pull down part of the transistor is made using NMOS. Okay, so NMOS is a not good pull up transistor. Now, what happens in case of VGS for PMOS? What happens in PMOS? In case of PMOS, to be on, VGS must be less than or equal to VTH, right? So now initially this is 0. So VGS is minus 5, right? So this is minus 10, and this is less than minus 1 volt, right? So this is on, and then this the 5 volt, this is like 5 volt is connected to here, so this is on. So this, you can say that it has a very low resistance, so it will charge up till 5 volt. Okay, now what happens if it's charged up to 5 volt? So VGS is again, it remains same, which is minus 10 volt, and it will not turned off, right? So that means our V1 in this case can be 5 volt. Okay, it will be a maximum of 5 volt, because that is what it is trying to, like this capacitor is trying to charge till that voltage. Okay, so this is like, this terminal is connected to this terminal, it's like that. So the PMOS can pull up the load to the VDD value. Okay, that is why these are a very good pull up transistor. You can try it for pull down transistor, where you will see that NMOS can pull down to a very low value, while PMOS cannot. Okay, so that is the advantage of using CMOS technology. This is not circuit course, but it was asked in the I think on earlier assignments, and it was asked in GATE also, so that's why I have included it. So yeah, to know how to manage time properly. Let's do it very quickly. I know it's 7 already. When I was discussing, I think in week 10 there was power cut here, so I could not discuss much of the question that I initially thought I will discuss. Okay, so this graph is given. This is the evolution of various technology nodes over the years, and these are we have to find out how the gate capacitance per unit area changes with technology nodes. Okay, so gate capacitance per unit area, COX, is epsilon OX by TOX. If we don't change the material, then epsilon OX remain constant, and if we scale TOX to alpha into TOX, then our gate capacitance changes from COX to 1 by alpha COX. Okay, what is the typical value of alpha? We scale it with around 0.7. Why we do it in 0.7? Ultimately, we want to reduce the device area with by half. Okay, so area is like W into L. If I consider only the channel length as my active device area, so if I scale both with alpha W and alpha L, then 0.7 into 0.7, so this is 0.5 into WL, this whatever. Okay, so the area actually reduces by half approximately if we do it. Okay, this is 0.7 is actually 1 by root 2. Okay, so what happens to gate capacitance? I don't know where I have discussed these things. Okay. Now what happens from 250 nanometer to 90 nanometer technology? So this is 250 and this is 90, right? So it is scaled by alpha times, this is scaled by alpha, and this is scaled by alpha. So whatever my oxide capacitance per unit area for 90 nanometer technology, that is equal to whatever my gate oxide capacitance for 250 nanometer technology, this is by alpha, right? So this will be by 3 alpha. Okay. Now instead of gate capacitance per unit area, you may be asked any other parameter of a MOSFET. Okay. This is a graph given, and according to this graph, this is the difference between a planar MOSFET and a tri-gate MOSFET. Okay. What happens to the transistor delay as channel current increases? Okay. So what happens to the transistor delay? What is delay? Delay is proportional to, delay is like tau, and we consider MOSFET is like a resistor and a capacitor, so the delay is equal to R into C. Okay, so C we know the capacitance, which is the total capacitance, and R resistance is V by I. Okay, so this the voltage we scale, and also we scale current. So with different technology, the delay changes, and how the delay changes, if you do the calculations, if you calculate the by using the scaling factors, you will see that with the scaling from one technology to another, delay is actually decreasing, and that's how we are making faster and faster devices. Now what happens in a planar and a tri-gate delay? What happens in planar means this is like a single gate. With double gate or triple gate, the configurations, those were discussed in the lecture video. If you don't remember, please go through it again. As the gate area, I mean the effective area of the gate control is increasing, that this is even true for FinFETs also. What happens in FinFET? We have these fields, and the gate is all around the fields. Okay, so overall the area of the gate, the gate has a more control over the channel area. Okay, if it is a planar technology, a portion of only a portion of the gate, effective channel length, that will be controlled by the actual gate. There will be charge sharing and other concept that will happen because of the nearby other reasons, right? So in case of like higher the next technologies of MOSFET, what people are trying to mean that they are trying to increase the gate control, and that is by increasing the effective area of gate around the channel. Okay, now when the gate is increased, the gate control is increased, so the drive current, that is due to the gate applied voltage, that increases. Okay, so you can see there is an increase in current. Okay, in the graph it is not given, but there is an increase in current because of the more gate control. Okay, VGS, it can create like a proper channel that can be turned on and off based on the gate voltage, not due to the charges or other kind of secondary phenomena. Okay, so ID increases actually. Okay. So because ID increases, you can see this delay is inversely proportional to current. So there is a decrease in gate delay compared to planar technology than in tri-gate technology. So what happens? Okay, I hope it is clear. If you have any quick doubt, you can ask. You don't have. It's already 7:09. If you have any quick doubt, you can ask. Otherwise, we will anyway meet on next Tuesday. Okay. There were a few more questions. I think I left. Yeah, 3 questions. We can take. We can keep these in the next session also. You are welcome. If there is no question, then I will stop the session here. Thanks for attending the session. I hope it was useful, and let's meet next Tuesday.